Introduction to Electrochemical Cells video. Let's start by considering what happens when we start with a beaker containing a solution of copper 2 plus ions, or containing copper 2 plus ions, and we submerge a piece of zinc metal in that solution. Well, over time, what we see happen is a sort of reddish-brown solid form on the surface of the zinc metal, and the blue color of the solution that contained the copper 2 plus ions fades. Well, what's happening here is copper 2 plus ions are forming copper solid, which is depositing on the surface of the zinc metal, and we can't see this, but zinc 2 plus ions are forming in solution. They're clear and colorless, but they are forming in the solution. We just can't see them. And so the reaction of zinc solid with copper 2 plus ions to make zinc 2 plus ions and copper solid occurs. It's an oxidation reduction reaction. Zinc is oxidized, it loses electrons. Copper 2 plus is reduced, it gains electrons. We form the products zinc 2 plus and copper solid, and all the electron transfer takes place at the surface of this piece of metal. The electrical energy produced is not harnessed, it's dissipated into the solution as heat. And so we'd like to be able to do something useful with the flow of electrons that's produced by this reaction. And there is a way to do this. So we can do this same reaction, but in a useful way, harnessing the electrical energy it produces by doing the following. So we use all of the species involved in this reaction, copper 2 plus, copper, zinc, and zinc 2 plus, but we make what are called half cells where the two components of a given species, so in this case let's say copper 2 plus and copper solid, are in one half cell in one beaker. We have a solution of copper 2 plus and a piece of copper metal submerged in it. And then we separate the zinc species, so we have a beaker containing a solution with zinc 2 plus and a piece of zinc solid metal submerged in it. And then these pieces of metal are called electrodes. We connect the electrodes with an external wire. Here the wire is going to go through a voltmeter, so we can see the voltage that this cell produces, but we could have a small light bulb here and use the flow of electrons to make the light bulb light. And then we need to complete the circuit using something called a salt bridge. And here the salt bridge are these connections between the two beakers where there's an electrolyte solution that's able to move between or flow between the two beakers to maintain the circuit as a closed circuit and enable the flow of electrons. Okay, so let's take a look at how this works. So here's our overall reaction. Here's a sort of schematic of the setup. We have a half cell containing zinc and zinc 2 plus, a different half cell containing copper and copper 2 plus, external wire connecting the two electrodes, and salt bridge connecting the two half cells to complete the circuit. And what ends up happening is in the copper half cell, copper 2 plus gains electrons to make copper solid, so copper is reduced. We call this the reduction half cell. And in the cell, copper 2 plus ions, when they gain electrons, form copper solid, which deposits on the surface of this electrode. So over time, the electrode actually gets larger, its mass increases, and the copper 2 plus ions in solution, their concentration decreases. In the other half cell, the other part of the redox reaction takes place. Zinc is oxidized, so zinc solid loses 2 electrons to form zinc metal. Form zinc 2 plus ions. Zinc then atoms from the electrode are, when they lose electrons, forming zinc 2 plus ions that go into the solution. The zinc electrode then over time decreases in mass, concentration of zinc 2 plus in the solution increases, and this is what occurs in the oxidation half reaction. Now, of course, for one substance, the copper, to gain electrons, we have to have another substance, the zinc, that loses them, but they also have to have a way to transfer, so that's the external wire here. And let's note that the electrode where oxidation occurs, we call the anode. The place where reduction occurs, we call the cathode. And the electrons flow from the anode spontaneously to the cathode. They're more easily lost by zinc. They're more easily gained by copper. And this electron flow now through the external wire is something we can harness. Now, a couple other things to note. The cathode is relatively positively charged by comparison to the anode, so it draws or attracts electrons more. Electrons are negatively charged. You can think of it as being more drawn towards the positively charged electrode. But when this starts happening, you get some buildup of negative charge over here and some loss of negative charge over there, and that won't continue unless there's a way for charge to continue flowing. And so in order to allow this to continue beyond just a few electrons, we have to have the salt bridge, which contains an electrolyte, so positive and negative ions. And negative ions from the salt bridge flow into the oxidation half cell to balance off the charge of the positive ions being produced by this oxidation half reaction. So more zinc 2 plus ions form due to the half reaction. Negative ions flow in to maintain charge balance. And then on the other side, of course, positive ions are being lost, so to speak, from the copper 2 plus solution. So more positive ions from the salt bridge have to flow in to replace them, in a sense, the copper 2 plus ions that are lost. And so that maintains charge balance. And so this electrochemical cell can operate spontaneously so long as all those features are in place. In this particular case, the voltage reading we get if the copper 2 plus and zinc 2 plus solutions are 1 molar concentration is 1.1 volts. This is a measure of the difference in potential between the two different metals. If we use metals other than copper and zinc, we can get the same type of electrochemical cell, but we'll have a different voltage reading because the different metals have different differences in their potentials. And we will also note that this is an example of an electrochemical cell that operates spontaneously. You just build it and the reaction will take place. And we call a spontaneously operating electrochemical cell a galvanic cell or a voltaic cell. Later, you'll see how the two half reactions add up to make the overall reaction, and the potentials of the half reactions contribute to the potential for the overall reaction. But that's a topic for another day.